Matter. What is matter? Not what's the matter, but what is matter? Matter is anything that occupies space and has mass. So, your textbook, your desk, my mouse, my Rockstar that I'm looking forward to drinking, takes up space, has mass. It's matter. If we look at a specific kind of matter, we call it a substance, where it's just, one kind of thing. So the water in my cup, we could call that a substance. It's matter. We classify matter by its physical form, which we call its state. Is it a solid, a liquid, or a gas? And also by its composition, meaning what components make up that particular kind of matter. We'll find out that scientists classify things a lot, and sometimes there's more than one way to classify things. And if you think about Legos, right? My house is overrun with Legos. We've been collecting Legos for like over 20 years now, so we've got lots and lots of Legos. They're so fun to step on, aren't they? But you can classify the Legos in different ways. One summer I got really crazy about, hey, let's sort the Legos so that we could actually build these things that we have all these cool instructions for. How do you sort the Legos? You could sort them by color, put all the green ones, all the brown ones, all the blue ones. You can sort them by shape. You can sort them by, are they the thick pieces or the really thin? The thin ones are a third as thick as the thick ones. Is it a special piece? I mean, there's different ways you can classify the Legos. And the same thing goes with matter. And the different classification schemes help us to make sense of all this information. Because if we just have facts, water boils at this temperature and this thing has a density of that, just random facts, we can't make sense of any of it. And so we classify things and we group them, and that helps us to make sense of things. So one way to classify matter is by the state of the matter. I think that was someone moving a stool. I don't know. We can classify it as a solid, a liquid, or a gas based on the properties that it exhibits. And we observe that matter changes from a solid to a liquid to a gas as the temperature increases. And water is one of those substances that we can observe in our everyday lives in all three states. We have ice and water, and as a gas we call it steam. So the atoms or molecules in the different states have different structures in those different states, and that leads to different properties. So if we look at a solid, the particles in a solid are often arranged in a geometric order. They don't move relative to each other, and that leads to the characteristics of a solid are that it has a fixed shape and a fixed volume. In a liquid, the particles are still very close together, but now they're able to move relative to each other. And we see that the characteristics of a liquid are different. The volume is constant, but the shape can change. In a gas, the interactions between the particles are different. They're now very far apart from each other. And a gas will have a variable volume and a changeable shape. And the properties of those three states are caused by or come from the different structures that the individual particles have. So in a solid, we've got all the particles packed closely together. One book I've used calls them touchingly close. Right? They're close enough they're touching each other. They're packed together in fixed locations. That doesn't mean that the atoms and molecules aren't moving, because they are. All atoms and molecules are moving, but they're vibrating in place. They're not moving around. And so I have an analogy for the solid state of students. Currently, you guys are in the solid state. You're all constant relative to each other, right? I don't know your names yet, but you are on this side of her, and you're not moving around, right? Now, is everybody perfectly still? No. I'm glad that you're breathing. Breathing's a good thing. Blinking, you're fidgeting a little bit. Some people are taking notes. That guy's, moving. It's fine. It's all good, right? but you're solid. You're not moving relative to each other. And that's what solid particles do. They move, they vibrate around, they're not completely still, but they don't move relative to each other. And because of that, fixed volume, rigid shape. The shape is not going to change. Examples, ice, aluminum, diamond. It's kind of silly. We can take solids and categorize them further, I should say. We can have crystalline solids or amorphous solids. By the way, when you see a word that's bold here, that's a term that I expect you to understand. There's a glossary in your book. There's always Google. I'm not going to test or quiz you on definitions, but I'm going to assume that I can use these words in a problem or a question on an exam and you understand what that word means. So we just need a contextual understanding. So a crystalline solid is like a crystal. It's got atoms or molecules that have patterns with long-range repeating order. Examples are table salt and diamond. Here's a picture of a diamond. And if we look at the atoms in a diamond, we see that they have a particular geometric shape. And that repeats itself throughout the diamond. And that gives rise to some of the characteristics of diamonds, that you can cut them and they have very, well, you don't actually cut them, they shear off, but they form these nice facets and they reflect light and they're very hard and all those good things. The other type of solid is amorphous. And we'll see that in science we have a lot of words with prefixes and suffixes. The prefix a means without. Morphous, what does it mean when a superhero morphs? They change shape. Amorphous, without shape. So an amorphous solid has no long-range order. This is kind of like a blob. The particles are just willy-nilly. Now, would you guys be crystalline or amorphous right now? You're not super crystalline, but I'd say you're mostly crystalline because we do have some order here. We're mostly in rows, right? If we all got up and just kind of stood here in the corner, then we'd just be sort of random and we would be amorphous. So glass is an amorphous solid and plastic is also amorphous. So is rubber. So liquid. In the liquid, we still have the molecules touchingly close. The densities of liquids and solids are pretty close, but now they're free to move about. So for chemistry students, the lab is when you are liquid, because we're still all in the same room, we're taking up the same volume, but now you're moving around. You're going to use the balance, and you're going to use the sink and get something out of the hood, and you're moving around. And that's why liquids have a fixed volume. The particles are still close together, and they're not moving apart and getting closer together, but it doesn't have a fixed shape. The shape can change. So the ability of liquids to flow allows them to take on the shape of their container. So water, alcohol, gasoline, those are substances that are liquids at room temperature. In the gas, there is a great deal of space between the particles, and the particles move freely and completely independently of each other. And we'll talk more about gases in a later chapter. So the gas state of students is when we're done with class and we open the door and you guys go off in all different directions, right? And there's a tremendous amount of space between you. You're just scattered all over the place. That's the gas state. The particles are moving, but they're not interacting with each other. And the distance between them can vary. And so the volume of a gas can vary, and the shape can vary. Because of the tremendous amount of space, a gas is compressible. If you put a liquid into a piston and you press down on it, not much is going to happen. Those particles are already close together. You can't squeeze them any closer. You put a gas in a piston and press down on it, and you can squeeze them together. That's why you don't want air in the brake line of your car, because it's based on a hydraulic system. It's got a fluid. You put pressure on one end, the fluid transfers the pressure to the brakes and make them stop. If you've got air in there, you put pressure on it, and it just compresses the air, and the brakes don't work. Not a good thing. So we can also classify matter according to its composition. So we were talking about its physical state. We can also classify it by composition. And so here's kind of the big picture, and then we're going to talk about it all individually. We've got matter. You can go pure substance or mixture, and then each of these has subcategories. Element and compound are both pure substances. Heterogeneous and homogeneous are both mixtures. So the first and largest division is between a pure substance and a mixture, and it's important to understand the differences between these. A pure substance is made up of only one component, and the composition is always the same. So you can't just mix more of one thing in. The composition is always the same. If it's, my example thing is broken in my head. Let's talk about the mixture. In a mixture, you have two components, and their proportions can vary. You could have a little more or a little less, like putting sugar in your tea. You could put 1 lump of sugar, or you could put 4 lumps of sugar. It's still sweetened tea, right? But the composition varies. I need something for the pure substance. Well, water is always a good example. So, crude picture of water. So water, we've got 1 oxygen and we've got 2 hydrogens. And if we were to look at water, all the particles of water are going to be the same. They're all going to have 2 hydrogen atoms, 1 oxygen atom, all together. So every single particle looks exactly the same. If we have a mixture, we're going to have at least 2 different kinds of particles. Okay? So you can make a mixture of hydrogen and oxygen where you put hydrogen gas and oxygen gas together. It's kind of dangerous because it explodes really, really well. But you can do that. Or you can combine oxygen and hydrogen in this particular ratio of 2 hydrogen to 1 oxygen, and that forms water. And the composition of water is always the same. Doesn't matter where you got it from. You can get it from the Nile or from the King's River. Purify it, the water is the same. The particles are all identical. So we can take that category of pure substances and break that down into elements and compounds. And this has to do with, can you take it apart into simpler substances? So an element cannot be chemically broken down into simpler substances. So it's the Lego brick. You can't take the Lego brick apart into smaller things. But a compound is a couple of Lego bricks together, or maybe a whole bunch of them together, and you can take it apart. You could make a compound out of Legos. Sometimes I actually bring Duplos in, but yeah, not on top of it today. I'm just lucky to be here. So if we had some strange child playing with the Lego bricks and making a bunch of these simple little things, a 2x2 red brick and a 2x2 blue brick, and you stick them together and just make a whole bunch of those, that would be like a compound. Because all the individual pieces, the particles that are not attached to each other, are the same. But this can be taken apart into something simpler. You can take it apart into a red one and a blue one. So compounds can be taken apart into elements. Elements cannot be taken apart. Most elements are chemically reactive, and they combine with other elements to form compounds. There aren't very many elements that you find in nature as elements. Most of them are combined with other things as compounds. So compounds are much more common than just free elements. So that was the pure substance side, and then the other side was the mixture, and we can categorize mixtures into two different groups, heterogeneous and homogeneous. And here we go with the prefixes again. Oh, I didn't want that. I wanted this guy. Hetero and homo. Homo is a prefix that means different, and homo is a prefix that means the same. And so we categorize the mixtures based on how the two or more substances within the mixture, how well they mix, how uniformly they mix. Is it the same throughout? Then it's homogeneous. Are there regions that are different? Then it's heterogeneous. So heterogeneous mixture is one where the composition varies. Mixtures are made of multiple substances. You have to have at least two substances. But in a heterogeneous one, you can see that there's more than one substance. So like if you mix sand and salt together, you can see, oh yeah, there's little bits of sand and there's the salt, and you can mix them all up, but you can still see the particles. It's not homogeneous. Portions of that sample are going to have a different composition than other portions. And some mixtures, like if you mix oil and water, they don't mix very well, right? And so you've got the oil on the top and the water on the bottom. Or if you have something like macaroni and cheese, you've got the cheesy sauce and then you've got the macaroni. And you stir that up all you want, there's noodles in there, right? The macaroni. It's different. It's heterogeneous. A homogeneous one, also multiple substances, two or more, but it looks like it's one substance. And all the portions of it have the same composition. If you take a cup of tea, you make tea, you put a tea bag in there, some hot water, and you throw in some sugar and you stir it all around, you take the tea bag out, and you stir it all up, and it's like this brown liquid, and the stuff on top is just as brown and just as sweet as the stuff on the bottom. It's homogeneous. It mixes uniformly. So we should be able to identify some common substances as being homogeneous mixtures or heterogeneous mixtures, or the other option is a pure substance. Now, some of these may not be obvious to you. I'll probably give you questions like this on an exam, but I will make them a little more obvious. Gasoline. I just hear murmurings. It is a homogeneous mixture, okay? It looks like it could be a pure substance. But you go to the gas station and they have these different kinds of gasoline. What's different about them? Octane. Octane is one component of the gasoline. And so some of the gas has a higher composition of octane than others. And so actually gasoline is just a tremendous mixture of different hydrocarbons. So that is, we'll call that HOM, homogeneous mixture. How about a stream with gravel at the bottom? That's a heterogeneous mixture. That one should be pretty easy. You've got the rocks at the bottom and the water. They're together. You could have more rocks or less rocks, and you see that there's two different parts to it. How about air? Well, that depends on what day in Fresno you're talking about, right? And when I drive in from Reedley, sometimes I'm like, wow, the air is really heterogeneous today. There's this yellow layer over Fresno, and then it's clear above, and you're like, ugh, right? Air should be. How about the air in this room? You see any particles in it? Chunks? It's pretty homogeneous. So we're gonna call air a homogeneous mixture. Brass. Brass is a homogeneous mixture. Brass is actually a homogeneous mixture of several different metals. It's a solid mixture of metals. But you take a real brass doorknob or something, and if you cut it in half, it's the same all the way through. A lot of the stuff, like the doorknobs at my house, they're not solid brass. They're like gold tone painted plastic or something, and it flakes off after a while. Real brass doesn't do that. Copper metal, that's a pure substance. PS, pure substance. Copper is an element, okay? So copper metal is just copper. If you were able to go in and look at all the particles, they'd all be copper atoms. Now in brass, you go down and look on the atomic level, and you'd see different kinds of particles, even though they're mixed together really well. Any questions? Another thing about mixtures is that they can be separated, because the components, being different substances, are going to have different physical and or chemical properties. And so you can make use of those differences and separate them. There's a variety of techniques. If you have sand and water, you can separate them by a technique called decanting, which means you pour off the liquid carefully. If you do it slowly, the sand will stay in the container and the water will come out. You've separated them because one's a liquid and one's a solid. A mixture of homogeneous liquids, more difficult to separate, but you can separate it by distillation based on differences in boiling points. So some things in the mixture are going to have higher boiling points and some are going to have lower boiling points. So you put your mixture in here and you heat it up, and the more volatile, the things that are easier to vaporize with the lower boiling points, they will go into the gas state first, and they're going to want to escape because that's what gases do. And so we're going to make them come out through this tube here called a condenser. It's actually a double-walled tube, and we run cold water through there. So it went into the gas state because it got warm, and now as it comes through here, we cool it down and it becomes a liquid again, and we can collect it down here. So that's one way to separate liquids in a homogeneous mixture. If you've got alcohol and water together, they mix together really, really well. How do you get them apart? Well, alcohol boils at a lower temperature, so you can distill it. An insoluble solid and a liquid. You could decant it, but sometimes the solid wants to come out with the liquid. You could use filtration. If you make coffee, you're filtering. Somehow you got to get the coffee grounds out of the coffee, right? So here's the water, and this is actually exactly how I make coffee for my husband, except I don't use the Erlenmeyer flask there. A big measuring cup, put the coffee in there, mix it with the boiling water, and then pour it through the Chemex coffee filter, which looks like a funnel attached to an Erlenmeyer flask. The water, with all the coffee goodness, I don't like coffee, but he thinks it's good. All the coffee goodness goes through, and all the coffee grounds stay here, separating based on difference in state, solid and liquid. And separating mixtures, I mean, that can have practical applications too. We had a big jar of change, big glass jar of change, and it lasted for a long time, and then someone broke it. And so here in my bathroom, I have piles of change, probably like $200 in change, and a lot of broken glass. Like, how do you separate broken glass from lots and lots of pieces of money, right? I made sort of a crude filter out of some mesh from the Lego set, and that allowed most of the glass pieces to fall through, but not the coins. Sometimes you can separate things with a magnet. You may have seen a demonstration of magnetic iron filings and sulfur, and you can mix them all together. Then you can use a magnet, and it'll pull the iron filings out. My son Michael does that a lot. He goes down to the river and collects sand, and then he uses the magnets from the fridge, and he pulls out. So now all the magnets on my fridge have all this furry iron filing stuff that he got from the river, and then it scratches up the fridge, and oh, good grief. I'll stop now.